Hello dear friends, welcome to my channels. Today's discussions is GATE 2017 topological space. So friends, this questions is very important that x and y be a topological space, okay, and if such that x tends to y be a continuous surjective function, and which one of the following is true? Number one, x is separable, then y is separable. X is first countable, then y is first countable, and x is Hausdorff space and y is Hausdorff space. X is regular and then y is regular. Okay friends, now we have to know that what is surjective continuous surjective functions. Okay, continuous surjective functions means 1 1 on 2. Okay, so we need to take some example. Okay, so in here we say it is given that f tends to y be a continuous surjective functions. So we can take example that f such that x tends to x, so it is continuous. This function is continuous function. Okay, continuous surjective functions. Okay, x tends to x. I hope it is not no problem, because x and x both are cardinality are equal. So continuous functions. Okay, so let now take x comma tau. X comma tau is discrete topological functions. Discrete topological functions. Okay, discrete topological space. Okay, very fine. Now we have to know that topological discrete topological space discrete topological space implies it is Hausdorff space. Okay, Hausdorff space. Another is regular space. It is also regular. And fast countable. Okay, fast countable space. What is fast countable space? That I have already discussed in my channel. Okay, fast countable space. Okay, fast countable space. Okay, discrete discrete topological space is equal to Hausdorff space, regular and fast countable space. Now if such that x tends to s is equal to fx is equal to x. Okay, discrete topology. Discrete topology. Now friends, we see that if such that a subset of x be open, then continuous property f inverse a equals to a subset of x. Okay, now if such that x tends to x, where x is discrete topology, x is discrete topology, and where x is co-countable topology. So co-countable topology is not regular, not regular. Co-countable topology is not regular, not fast countable, not regular, not fast, not regular, not fast countable. Not fast countable topology. So friends, when it is co-countable topology, then it is not regular, not fast countable topology. So friends, according to the questions, x is fast countable, y is fast countable. This portion is wrong. Why? When x is discrete topology, then co-countable topology is not fast countable, and x is Hausdorff. That means it is okay, and x is regular. Okay, x is regular, then it is not y is then y is regular. This is not correct, because x is discrete topology, then it is regular, but co-countable topology is not regular. Okay, another is, sorry, surjective map function is onto function. Okay, surjective function is onto function. Suppose if such that x tends to y, x is discrete topology, then y is indiscrete topology. Okay, this kind of map is possible onto map. So indiscrete topology, and indiscrete topology is not Hausdorff. Okay, this is not Hausdorff. So option C is not correct. But if x is separable, then y is separable. Okay, this is possible. How friends? Because what is the meaning of separable? Separable meaning of the separable is number of finite dense set. Okay, countable dense set. Finite dense set. Finite is countable. So there is a theorem. There is a theorem, a mapping f from a space x into another space into y, another space y, is continuous. Okay, is continuous if and only if a closure subset of f a closure. Okay, f a closure and total f a closure. Okay, so for every Okay, now for every a subset of x, okay, and for all a subset of x. Now all a subset x, suppose x is separable, okay, x is separable. So if is separable, then a subset of x be countable dates, countable dates, okay, it is countable dates. Then a bar equals to capital X if such that a if by mod of a, if a equal to less than equals to a, okay, so if a is countable, so a bar a closer equals to x, and if such that a tends to be mod of fa, so fa is, then fa is countable, okay, countable. So if a bar subset of if a whole bar equals to fx, then if a whole bar subset of y bar equals to a y. So another way that if a bar, if a means closer subset of y, then y equal to if a bar, okay, total closure, if a closure of if a, okay, it can be say closure of if a, then which proves that y is also separable. Suppose x is separable, then y is separable, so my option a is correct. Option a is correct. Thanks for watching. I hope this solution you like. You like the solutions?